Perfect. Thank you. Thank you very much for this very kind introduction. It's really a pleasure to be here, and thank you the organizers for putting this all together. So as you mentioned, what I would like to share with you today is some of my work that I did during my PhD at NUS, and that was mostly related to developing a phase field model of grain boundaries, and then coupling grain boundary evolution with some other mechanisms within the grains. So I did my PhD at National University of Singapore, and that was also supported by ASTAR, Agency for Science, Technology and Research. So I actually had 4 supervisors during my PhD, Jerry Quake, Rajiv Aluvalia from ASTAR, and Pro Shailendra Joshi and Pro T.T. Okay, so I decided to divide the presentation into 3 or 4 parts. I would first introduce the phase field model, KWC phase field model. That is a phase field model that we started with, and then we built on top of that. And after that, I will start with a simpler example of martensitic transformations in nanocrystalline shape memory alloys. And after that, I will introduce phase field model that is coupling intra-granular deformations, whether it's plasticity or deformation twinning with grain boundaries. And I summarize with some future perspectives. Since I'm not sure how are you actually familiar with phase field models, so I will just very briefly introduce the basic concept. And especially here, we try to use phase field model for modeling grain boundaries. So in a phase field model, these are actually these are fantastic tools if we want to study, let's say, materials that contain a lot of interfaces. So they have large network of interfaces, such as polycrystals, or we have certain phase transformation, such as martensitic phase transformation, where we have austenite martensite interface, or formation of precipitates, and many such examples. We can use phase field models because the advantage here is that we don't have to care too much about the interface. We don't have to explicitly track the interface, such as is done in sharp interface models, but all of that information will come out sort of naturally from the phase field model. Nucleation, annihilation of that interface, growth and interaction of interface. And the basic idea in developing phase field model is to construct the energy function, such as illustrated here, where the energy functional is a functional of certain fields called the order parameters. For instance, here we have one order parameter, a parameter called eta and theta. In the very basic phase field model, the order parameter basically describes the phase. It's usually attributed to values 0 and 1, where 0 may represent the parent phase and 1 may represent the product phase. So we can study the transformation from the parent to the product phase. And anything between 0 and 1 is basically representing the interface of those 2 phases. Right. So the phase is described by the order parameter that may be one of these 2 values, and that's described by some term that is called the chemical energy. And additionally to this, we also add additional term that represents the interface itself and the energy of the interface. So that's the higher order term, the gradient of that order parameter. And this is related to the energy of the interface, and it also diffuses the interface itself. So the interface itself is of certain width, but that can be numerically adjusted based on the numerical scheme. So that would be the very basic phase field, these 2 first terms here. In order for us to model grain boundary, there are 2 families of phase field models that we could use. The first one was proposed by LQ Chen and coworkers, where you actually assume each grain orientation as a separate phase. So we introduce as many order parameters as you have grain orientations. So that's sort of a disadvantage of that model. Eventually, you have to solve a lot of equations simultaneously. And the other family of phase field models are those proposed by Kobayashi-Warren-Carter that I'm presenting here, where you have the phase field model that operates only with order parameters, with eta and theta here. And with only 2 order parameters, you can describe any polycrystal with as many grains as you wish. So that's the very attractive feature of this phase field model. And additionally, to model grain boundary migration, the model also allows you to do grain rotation. That is another interesting feature especially something that is observed in nanocrystalline materials, where the grain boundary migration is not the only mechanism of grain coalescence, but it may be also grain rotation. So basically, Kobayashi-Warren and Carter, they proposed this phase-fold model. This is the free energy functional that basically represents the grain boundary energy itself. And in phase-fold model, what we do, we simply minimize that energy functional within some kind of framework, for instance, Ginzburg-Landau theory. And by minimization of that function, we arrive to a set of equations, such as illustrated here, that we solve in time and space, and this will basically give us the evolution of these order parameters and evolution of that grain microstructure. The meaning of these two order parameters that I'm describing here are theta, that's the easy to understand. Theta is basically grain orientation itself. So here we have a schematic of a bicrystal where we have two grain orientations, and this is the grain boundary. And then eta represents, it's called the crystallinity order parameter, and it represents a certain amount of disorder. So if the crystal lattice is perfect without any defects, the eta is equal to 1. If there are any defects, let's say there are dislocations or grain boundary itself, then eta is less than 1. Not necessarily 0, but somewhere between 0 and 1. So it sort of introduces some amount of disorder within the crystal itself, in this case, the grain boundary. And the very interesting feature of these models is when you look at the second equation here, you may recognize is that this equation is actually a diffusion equation. And I highlighted the diffusivity constant here. That is basically the gradient of the grain orientation. And you can see that the grain orientation is constant everywhere except that grain boundary region. So what you end up having is basically diffusion equation. You are solving diffusion equation with infinitely large diffusivity on most of the domain where you are solving these equations. So these equations are called also equations with singular diffusivity. It's a very interesting problem described in these 3 publications here. It's a little bit tricky to do this numerically because of the singularity term, but there are ways how to do it. And we've implemented finite difference method as well as finite element method, and it was working just fine. Right, so this is the basic model that we started with and was proposed by Kobayashi-Warren and Carter. So now we have a model that we can use for representing grain boundaries in a certain way. And sort of the first problem that we looked at are martensitic transformations. And we looked at the martensitic transformations in shape memory alloys. So we know that martensitic phase transformation is a very important phase transformation. In steels, for instance, we know martensitic steels, maraging steels, that gives us a lot of good mechanical properties. Then we also see martensitic transformations in shape memory alloys, where we have this shape memory effect or superelasticity at higher temperatures. And even biological systems, such as this virus bacteria page, it can be shown that its primary living functions are actually resembling something martensitic transformations. So now I will focus only on shape memory alloys and specifically for nanocrystalline materials. It has been shown experimentally, and what motivated this study is that as you decrease your grain size, you go from polycrystal to nanocrystal, the martensitic transformation becomes suppressed. And that's something that is not very desirable because you lose your shape memory effect or your superelasticity behavior. On the other side, as you decrease your grain size, usually this is done in order to improve the strength. When you think of the Hall-Petch strengthening or improve the mechanical properties, we end up having this anti-correlation between mechanical and functional properties. And so we were trying to look into this issue a little bit more using a phase-fold model. So initially, we wanted to develop a phase-fold model that is able to reproduce this suppression behavior. And then we wanted to investigate less conventional grain size distribution to allow us to investigate this process. And there, we can come up with some distributions where we can recover the functionality and retain the good mechanical properties. Here we have another example from another publication by Waits, where we see polycrystal with 2 different grain sizes. And in the larger grains, with the martensitic transformation, there are 2 variants that formed. As the grain size decreases, we end up having just 1 variant. And eventually, if the grain size decreases even more, below 50 nanometers, the phase transformation is completely suppressed. Okay, so in order for us to model this using a phase field model, we establish a very simple phase field model of martensitic transformations. That model has been used by many researchers. It's actually quite simple, where the total energy can be, or sort of the total energy density can be additively decomposed into a chemical part that is temperature dependent and tells you what phase, whether the austenite or the martensite is stable at that particular temperature. So it looks like a double well. Then we have the gradient term that I explained on the slide that is basically related to the energy of the interface. In this case, the energy of the austenite-martensite interface. And since we are dealing with a phase transformation, and this is a displacive phase transformation, for instance, from FCC to BCT, because of the change of the crystal lattice, there will be stresses that generate, and we need to account for these stresses as well. So this is accounted for using this this is basically strain energy. And if we stopped here and we just used this phase field model as constructed, we would not be able to predict the suppression of the phase transformation as we decrease the grain size. So my advisor, Rajiv Alvalia, he proposed an additional term into the energy functional that was published here in 2015, where he accounted for extra energy penalty at the grain boundary. What it means actually is that you may consider your grain boundary to be either martensitic grain boundary or austenitic grain boundary. And we hypothesize the martensitic grain boundary costs more energy than the austenitic grain boundary, then the phase transformation will be suppressed because the grain boundary itself would rather remain in the austenite rather than in the martensite. But if the grain interior would transform into the martensite, then we end up having the austenite-martensite interface at the grain boundary. And then this term will come to play. And because of the increase of the total interface energy with the decreasing grain size, we may actually suppress the phase transition completely. So this is how we can actually incorporate this effect thermodynamically within the energy itself, the total energy of the system. Here we just expand those energy densities. I won't talk much about this unless there will be some questions. And as I mentioned before, all of these energies minimized using the Ginzburg-London theory. We arrived at the kinetic equations, and we solve all of these equations with the mechanical equilibrium that we satisfy at every time step of these equations. So here I have an example or sort of illustrations of how we incorporate this extra penalty, extra grain boundary energy term into this phase field model and what it actually represents. So here I have a sort of gradient grain size distribution where you can recognize grain boundaries here. On the right side, we have larger grains, on the left side, smaller grains. And what I show here is this extra grain boundary energy difference between the martensite and the austenite. So this is basically this term highlighted here. This was basically generated using this KWC phase field model. And what you can see is that this energy difference is misorientation dependent. So we have also low angle grain boundaries and high angle grain boundaries. And you can easily imagine that when having low angle grain boundaries, we can assume that these are basically arrays of dislocations. The lattice is almost perfect, besides having those dislocations there. So low angle grain boundaries would probably not suppress the phase transformation. But high angle grain boundaries that may be considered almost as a highly disordered phase on its own would most likely suppress the phase transformation. So all this information is accounted for here as well. And now how this energy penalty actually changes the energy functional itself. If we are within the grain interior or at low angle grain boundary, we have this blue curve here, the blue double well, for that particular temperature, which tells us that the martensite is the stable phase. The system would transform into the martensite phase because it costs less energy. What I basically plot on the y-axis is the energy, and the delta GM is the energy difference between the two phases. And as we go to the high angle grain boundaries, as illustrated here, we would see this red curve. So from double well, we actually get a cell well, where only the austenite can exist at that particular temperature, unless we would decrease the temperature even more. So here we get suppression of the phase transformation, and the grain boundary would actually remain in the austenite phase, the remaining grain could potentially transform into the martensite. So this is the implementation of the grain boundary energy penalty. And here I have a couple of examples of some of the simulations that we performed using this model. Here I show 3 different examples of RVEs of 3 different grain sizes. So we have an example with grain size of 100 nanometers, 35 nanometers, and 50 nanometers. We took initially austenitic system. So we started with austenite that we quenched from 290 to 20 kelvins. And once this transformation, once we reach the equilibrium, this is what I basically show here, the equilibrium microstructure after the quenching. In this case, I'm looking at quite simple shape memory alloy, that is iron palladium, and all the simulations are done in 2D. So we have this martensite phase that is represented by 2 variants here, because that's FCC to BCT phase transformation. There are the 2 variants, red and yellow color, and then the austenite is the blue color. So that's the initial phase. So we can see that for large grain size, when we have polycrystalline materials and we quench it to lower temperatures where the martensite stable phase, we see the formation of the martensite, we see those twins here, even within those grains, if the grains are large enough. But we also see that there is residual austenite, especially near the grain boundaries and triple junctions, which may not necessarily be because of that energy penalty at the grain boundary, but it may be also because of stress concentrations that arise because of the evolution of those phases. As we decrease the grain size to 35 nanometers, we see that suddenly we don't observe within those small grains, but each grain is of its own martensitic variant. And we see also more of the austenite, especially at the grain boundaries. And as we continue decreasing the grain size even more, now we see that we completely suppressed the phase transformation, the effect that we wanted to achieve. So here the whole system is in the austenite with the very small grain size, 15 nanometers. So we can use this model to also predict the critical size when the transformation is suppressed and look at some other interesting things as well. Right. So as I mentioned earlier, with these, what we can see here is the suppression effect. So the loss of functionality. In the case of 50 nanometers, it's not a shape memory alloy anymore, because there is no phase transformation that is necessary for the shape memory or superelasticity. However, the mechanical properties may be improved. And so we looked at some other less conventional grain size distribution, now using this model to see what is the process of phase transformation. For instance, we started with bimodal grain size distribution, such as illustrated here, where we have a combination of large grains and small grains. So we have grains, equiax grains of size of 100 nanometers, and then we have small grains of 50 nanometers. And again, we do the same quenching process, and we just look at the phase transformation and at the equilibrium solution for this particular system. So we see again that the martensite is formed within the large grains and mostly suppressed in some of the smaller grains, but some of the small grains still do transform into the martensite. And this can be explained from basically from the stress field and stress concentrations that generate near the grain boundaries and near the triple junctions. If I zoom into this region of this white square, I can basically show the evolution of the martensite in time, how it proceeds. Right. So we have this bimodal distribution here, and then the evolution of those phases. So beginning from the left, we see that the martensite starts to form in the large grains. Here we have this large grain denoted by 1, and then it proceeds through the layer of small grains, and then it nucleates in the larger grain. But as it proceeds through this layer, there are also these stresses that basically those stresses at the interface that make or sort of are additional driving force for the phase transformation also in the region of the smaller grains. So this is sort of the mechanism by which we observe this phase formation here. And it's a very interesting problem, actually. So with this phase field model, we can look at and compare various grain size combinations, different grain size distribution, and see what's the mechanism of phase transformation, And this is the basically amount of shape memory or super elastic effect that can be achieved using such grain size distributions. Okay, so here I show you these grain size distributions. I didn't mention how we actually generated these polycrystals or nanocrystals here. What you can see here, these are actually Brno tessellation grains. This is done by algorithm developed by Czech. But if you would wish to use this kind of grain size distribution in some of your studies, there's actually a simpler way how one can do this using even simpler phase field model proposed by Chen. That is a phase field model of grain boundaries where you assume that each grain is a phase on its own. That's the first family of phase field model that I mentioned earlier at the beginning of my presentation. And you can generate these bimodal grain size distributions by setting two nucleation events. So just illustrated here, where on the left side, I show the this order, these are the grain boundary. On the right side, I show you the grains themselves. So as they grow, after the nucleation event, we introduce the second nucleation event. And as these are growing, we actually end up having a bimodal grain size distribution. And this can be done also in 3D very easily. So it's probably the most simple approach how we can actually generate this kind of RV with bimodal grain size distribution and use them for the studies of, let's say, martensitic transformations, as I illustrated now. Okay, so in the first part of the presentation, I presented a phase field model of martensitic transformations, and I illustrated how martensitic phase transformation is affected by grain boundaries, especially in nanocrystalline materials, where we have huge network of grain boundaries, and the transformation is suppressed. But as you noticed, I assumed that the grain boundaries do not evolve. So we assume them static. We assume that the martensitic transformation is very fast, and the grain boundaries simply remain as they are. But this is not the case in nanocrystalline materials. When we zoom into nanoscale and we decrease the grain size, we actually see a lot of grain boundary migration. And not only that, also rotation. And with this, we also see a lot of mechanism taking place within the grain, whether it's plasticity or it's phase transformation or even deformation twinning. So all of these mechanisms in nanocrystalline materials take place at the same time. They co-evolve in a certain way, and often they compete to relax the stresses. And so usually all of these mechanisms are previously modeled separately. So we have a model of grain boundary migration, model for grain rotation. We have some plasticity model. But what we wanted to achieve here is to develop a phase field model that sort of links all these mechanisms within one unified phase field framework. Grain boundary migration, diffusion accommodated grain rotation, and some plasticity within the grains, whether dislocation plasticity or deformation twinning, or even phase transformation, such as martensitic phase transformation. So that's the sort of the idea that's illustrated in this schematic here. And here we again proceed with a phase field model. So we built on top of the KWC phase field model again, that was used only for grain boundaries, right? This is what we use for sort of generating that grain boundary energy that is misorientation dependent for martensitic transformation simulations. So now we use this phase field model and we extend it by additional energy contribution. That's the elastic energy or strain energy density as illustrated here, that may be also dependent on the plastic deformation. So we may also account for certain plasticity model, such that we are able to model some intra-granular deformations. And as the first order approximation, we didn't really go into crystal plasticity. That would probably be the best plasticity model dealing with single crystals, but we wanted to have something simpler. So we decided to use Hill yield homogenized plasticity that is easier to implement, but there is still some sort of anisotropy that could provide us some insights of how these systems are evolving. So we've incorporated the KWC phase field model, added this energy term, and assumed Hill yield plasticity. And again, we minimize all of this within the Ginzburg theory. So we obtain the gradient flow equations for the salinity field, orientation field, and then also we have the equation for the plastic evolution. And all of this is solved assuming the mechanical equilibrium, divergence of stress at every time step as we solve these equations. And again, I don't want to spend too much time on these equations unless there will be some questions, but I would just jump into a simple example to illustrate the capability of that model and what we are trying to solve here. So here we have a simple bicrystal. It's a nanopillar, bicrystalline nanopillar, where we have two grain orientations. And here we have two boundaries. So these are strain boundaries. There is no curvature, which means that these grain boundaries would not move unless we apply certain mechanical loading or a certain stress. So here we apply displacement controlled deformation, and we simply load this nanopillar. And because we introduce certain level of stress, we should see grain boundary migration, because certain grain orientations would store less energy than the others, because this is still anisotropic, even in elasticity as well as in plastic regime. So having this example, here we have a simulation result where I show 3 panels. On the left side, I show the evolution of plastic strain component, XX in this case, evolution of the total strain in the middle, and then the von Mises stress in the right panel. And as you can see, as we apply this deformation into the nanopillar, the grain boundaries start to move. They are moving because this mechanism relaxes the stress, so it minimizes the strain energy. And then we can see here, when we look at the von Mises stress, we see the stress is going down. Initially, we see also some plastic strain formation as the grain boundaries move, but as the stress falls below the yield stress, there is no more of plastic strain evolution. But grain boundaries are still moving because the stress can go down and we can still relax the strain energy. Eventually, when the grain becomes extremely small, there is grain rotation that takes place. So the grain itself would actually rotate, and from bicrystal, we obtain a single crystal. But the grain coalescence is not due to the grain boundary migration, but it's because of grain rotation for these very small grains. And we have at the end a single crystal. So this is what the model itself can do and what kind of problems that it can be applied to. We can also look at the stress strain curves as we do the loading for different strain rates. And for this particular bicrystal, we see this interesting thing here where we have this dip in the stress strain curve. And that's exactly because of the rotation. So when the grains is very small, the rotation is much faster than the rate of loading. And so the stress is relaxed, and then single crystal is formed. And then we just continue loading single crystal. And we can use this model, of course, and apply it to much more complex systems of many grains, not just two. This is just illustration of sort of the capability of. Right, so here we have the grain boundary migration and some form of plasticity within the grains. And what we assumed is some homogenized plasticity model. But again, as we go to the nanoscale and we deal with the nanocrystalline grains, dislocation plasticity is actually, the conventional dislocation plasticity is not really taking place in nanocrystalline materials. And especially, that is actually very interesting because materials such as aluminum or palladium are high stacking fault energy materials. So you would never actually observe deformation twinning in these materials unless under some extreme conditions, extremely high strain rates or very low temperatures or nanocrystalline materials. So when you have these materials and you look into the nanoscale, you actually see formation of deformation twins instead of the dislocation plasticity. And this is very interesting. It was actually first time observed by atomistic simulations performed by Jakub, as we see here, a snapshot of that, where this deformation twin basically nucleate from the grain boundaries. These are basically partial dislocations that nucleate on adjacent planes. And 1 year after that, that was actually confirmed by experiment that it really is the case that deformation twins are forming in nanocrystalline materials. And that's the basically dominant plasticity mechanisms within the grains. So we continue with the framework that we already developed, but now we introduced the deformation twinning mechanism taking place within the grains and then letting grain boundaries evolve simultaneously with the deformation twinning. And grain rotation, of course, may be there as well. So we established the total energy functional as we did before. Now we have the grain boundary energy that comes from the KWC phase field model. We have the elastic energy because we're dealing with deformation twinning. It's similar to martensitic phase transformation, where we have the phase transformation from austenite to martensite. But in the deformation twinning case, it's basically, we consider it as two phases, as sort of twinned and untwinned phase. And with this energy functional, as we minimize this, we are able to solve and sort of co-evolve deformation twinning with grain boundary migration. I will again skip all of these equations. All of these details can be found in the thesis, but I will proceed again to another example that clearly illustrates what we are trying to model here, and how it's done. It's using this phase field model. So here I have a simple example where I illustrate seasonal grain RVE. This is a periodic RVE. We see the grain boundaries here, and then we apply pure shear loading into this RVE. What we would see is the formation of the deformation twins. We can already see that there is deformation twin that nucleates close to this triple junction and close to this boundary. But we would also see the growth of the grain boundary, an evolution of that grain boundary. So I have a movie here that illustrates the whole process of what's happening here. Right, so this is it. So we apply this loading, and what we see is formation of deformation twinning simultaneously with the evolution of grain boundaries. So I will play it one more time, maybe a little bit slower. So as I illustrated at the beginning, we have the formation of the deformation twinning that relaxes the strain energy for this particular grain configuration. And the grain boundaries are also evolving. We see that they are growing, particularly this grain in the center. This is the grain orientation that stores the least amount of energy. And so this one is growing and the rest of the grains are shrinking and disappearing at the end. So deformation twinning initially forms because it relaxes the stress for this particular grain configuration. But because the grains are evolving as well, the stress is also relaxed by the migration of the grain interface. And so there is no need for the deformation twinning to be there. So we observe the twinning process and we see that this twin is suddenly disappearing. And eventually we end up having a crystal. So all the grains sort of disappeared. Then we have this bicrystal here. These are periodic boundary conditions. And eventually we have curvature-driven grain growth. Okay, there is strong curvature here. For very small grains, there would be grain rotation, and eventually we end up having a single crystal. Okay, so I will play this once again. So we see that the phase field model allows us to do coevolution of deformation twinning within the grain simultaneously with the grain boundary migration. And eventually we get single crystal because that's sort of energetically the best solution. That's basically the solution that minimizes the energy the most. Okay, and of course we can look at more complex system, such as in this case we have again some sort of nanopillar where we have more grains and we do displacement controlled loading. And again, I have a video that illustrates the process of what's happening when we have the coevolution of the grain microstructure as well as twinning. So we see the formation of deformation twin at the beginning from the regions with high stress concentrations, which in this particular case is this corner here. And then because of different grain orientation, these twins may be, sort of the growth of the twin may be inhibited, but new regions, new twins nucleate from triple junctions and grain boundaries. And then we see sort of coevolution of twinning and grains as well. So that's the illustration of that phase field model. And very interesting thing here is that when you look at the grain orientation, you can see that actually those grain boundaries were moving much faster in the region that there's twinning, unlike in the region that did not show any deformation twinning here. Right, so that was actually my last slide here. So what I presented today, or what I was trying to show you, is that as we go to the nanoscale and we deal with nanocrystalline materials, we observe a lot of interesting properties, such as, and a lot of interesting behavior, suppression of martensitic phase transformation, deformation twinning that we would not really observe in polycrystalline setup, evolution of various mechanisms, grain boundary migration, grain rotation, intra-granular deformation. So it's a lot of interesting things that we can see in crystalline materials. And what I presented is a phase-float model that we were trying to develop to describe some of these mechanisms and coevolution of some of these mechanisms at the same time. So with this, I would like to acknowledge NUS and A-Star that supported me and studied during my PhD, and also my advisors, Jerry Quek, Rashid Alibali, Rafalendra Joshi, and Prof. T. Tay, and also acknowledge our very useful discussions with Prof. David Strolowitz. And with this, I would end my presentation and thank you for your attention.